Hello all, welcome to lecture number 12 for the ATM005 series. Today we'll be talking about atmospheric dynamics. This actually kicks off a two-lecture series talking about the dynamical character of the atmosphere, which specifically describes how air moves around in the atmosphere. This is somewhat different from what we've talked about previously, which focused on what is known as the thermodynamic aspect of the atmosphere, which is basically related to how temperature affects the atmosphere. So, in order to get to the heart of atmospheric dynamics and why we have air moving around at all, we need to first go back to this concept of temperature gradients. And specifically, we're going to be talking about the variation in equator to pole temperatures that naturally arise in the atmosphere because of this uneven heating of the Earth's surface. Recall back to our discussion about insolation, that because of the fact that the sunlight hits at an angle at higher latitudes, this means that you have less sunlight being received per unit area, and consequently you end up with colder polar regions and warmer equatorial regions. If this was the case that basically you had local radiative balance, that is, if you had that the net loss of energy from the Earth's surface had to match the net gain of energy at each latitude, that would lead to a very significant temperature difference between the equator and pole, because there would be, particularly during the winter time, absolutely no energy received in the polar regions. Consequently, the Earth has a means in order to actually deal with that through the redistribution of temperature and energy across the Earth's surface. This redistribution of energy, specifically the transport of energy from equator to pole, occurs through a process more commonly known as weather in the atmosphere and ocean currents in the ocean. Weather patterns generally arise because of four main reasons. First, we need to have that the Earth has an atmosphere. This is of course important because if we didn't have an atmosphere, there would be no air in order to move around. The dependence of insolation or sunlight on latitude then creates these temperature and pressure differences between equator to pole and provides a mechanism by which redistribution can occur. Then rotation of the planet gives rise to Coriolis force, which we'll see later plays a very important role in determining, for instance, the direction of the storm track, which in turn is responsible for the net west to east movement of air that we typically observe in the mid-latitudes. Finally, the fact that there's water in the atmosphere leads to rainfall and snowfall, commonly associated with weather patterns. Weather is then associated with what is known as atmospheric dynamics, that is, in some sense, how the atmosphere behaves like a fluid. There's actually a whole discipline that explores atmospheric dynamics more generally, and it requires a very intensive study of mathematical equations that govern the fluids of the atmosphere. Now, I'm going to avoid going into details about these mathematical equations, although I do have a series of YouTube lectures which you might be interested in if you really want to delve into the mathematics of it. Instead, I'll focus on a qualitative description of why the atmosphere behaves the way that it does. So how do we understand the dynamics of the atmosphere? What gives rise to features like tropical cyclones or extratropical cyclones or atmospheric rivers or other large-scale circulations in the atmospheric system? Well, it turns out that the atmosphere can actually be described very readily in terms of very basic physical principles, namely ones that you would typically learn in, for instance, a high school physics class or even a first-year physics class. So the first of these basic physical principles is conservation of mass. Conservation of mass effectively says that in a closed system, mass is not created nor destroyed. The total mass of the atmosphere in this case is to a very close approximation constant over time periods of interest. This also means that you can't have local mass sources. That is, any mass that occurs in a particular location must have gotten there via transport from somewhere else. The only way that mass can be changed is through, for instance, chemical reactions in the Earth's atmosphere. There are other mechanisms by which the mass of the total atmosphere can change. For instance, through a process known as hydrodynamic escape, we know that the atmosphere can actually escape through space over very long time periods, but this is a very slow process. We also know that through a process known as outgassing, gases contained deep within the Earth's surface are able to escape into the atmosphere and can replenish gases within the atmosphere as well. However, this is also a very slow process, and so for the purposes of weather timescales or even hundreds of year timescales associated with near-term climate prediction, these processes are irrelevant. The second physical principle that we use to describe the atmosphere is conservation of energy. This basic principle says that in a closed system, energy is not created nor it's destroyed. However, energy can transition between different forms of energy, including thermal, for instance, energy that describes the temperature of a system, kinetic energy, which describes the motion of an air parcel, mechanical energy, and potential energy, which is associated with raising air parcels up to higher altitudes. This principle is effectively enshrined in what is known as the first law of thermodynamics, and it describes a relationship between pressure, density, and temperature within air parcels. Another basic physical principle that governs atmospheric motion is Newton's second law of motion. This principle effectively says that acceleration experienced by an object, in the case of the atmospheric fluid, this object is an air parcel or a balloon of air, that the acceleration it experiences is equal to the sum of forces acting on that object. So in order to understand how an object accelerates or responds to its fluid around it, one simply needs to enumerate the list of forces that act upon that object and calculate what the total effect of those forces are. This is enshrined in a principle of conservation of momentum, namely, with no external forces, momentum of an air parcel must be conserved. So the three forces that act on these air parcels and consequently can give rise to motion of the atmosphere are the pressure gradient force, which occurs because of differences in pressure in two geographic locations, the Coriolis and the centrifugal force, and the gravitational force. We're going to see that in the horizontal direction, that is, for movements horizontally, the first two are the most important, whereas for vertical motions, the first and the third are the most important. So let's discuss how the pressure gradient force works. Basically, you can imagine this as follows. If you have a bathtub which has high water on one side and low water on the other side, and some sort of dam in between that prevents the high water from flowing into the low water region, the water in some sense wants to equilibrate. It wants to move from the higher level to the lower level because of a pressure difference between these two locations. If you were to remove the dam blocking the flow from high to low, what you're going to get is a rushing of water from the high water level region into the low water level region. This force, or difference between the pressures in the high and the low region, is known as the pressure gradient force. This is a good description, I suppose, for shallow water motion, but if you consider the atmosphere, the behavior is slightly different, but the idea is essentially the same. In the case of an atmospheric fluid parcel, here depicted with a cylinder, if we have high pressure to the left and low pressure to the right, effectively what this means from a molecular standpoint is that there are either more air molecules on the left that are bouncing against the fluid parcel, or those air molecules are traveling with a higher velocity, that is, they have a higher temperature associated with them, and so carry more energy when they hit that left-hand side of the fluid parcel. With low pressure on the right-hand side, effectively that means that we have fewer air molecules, or those air molecules are moving slower. This means that there's more force being induced on the fluid parcel from the left than there is on the right. Much like even macro-sized objects, you can imagine this, for instance, with tennis balls being thrown at a balloon or thrown at some larger object. If you have more action occurring on one side than on the other side, you're going to get a net acceleration of the object. That is, the object is going to tend to want to move from high pressure to low pressure because there's more pushing it on the left-hand side than there is on the right-hand side. So pressure gradient force in this sense works much along these lines in the atmosphere, and consequently leads to an acceleration of the fluid parcel from high towards low. On meteorological maps, you can actually see high and low pressure regions very commonly. So high pressure regions are usually indicated with a capital letter H, whereas low pressure regions are indicated with a capital letter L. So you can imagine that if you had a fluid parcel sitting in the H region, it would be experiencing a pressure gradient force that is attempting to push it towards the low pressure region. This is not actually what occurs in reality, for a reason that we will discuss shortly. So the second force that is important for motion of the atmosphere is the Coriolis force. Coriolis force is actually an example of what is known as an apparent force. That is, it isn't really a real force in the sense of something acting on the air parcel, but instead it's a force that is perceived by us standing on the surface of the Earth because of the fact that the Earth itself is rotating. Namely, air parcels still want to move in effectively a straight line. But what is a straight line to an observer far out in space is not a straight line to what we observe on the surface of the planet. In fact, the Coriolis force makes it look as though, in the northern hemisphere, air parcels want to move to the right, or they want to turn to the right, whereas in the southern hemisphere, it makes it seem as though air parcels want to turn to the left. So the Coriolis force effectively deflects fluid parcels away from moving in a straight line, and this is purely a consequence of the Earth's rotation. If the Earth was not rotating, there would be no Coriolis force present. The Coriolis force and the pressure gradient force together give rise, actually, to the study of a branch of fluid mechanics known as geophysical fluid mechanics, and it's a principal discipline for the study of atmospheric science. There's a video on the Canvas site, actually, on the Coriolis effect that should give you some intuition as to why the Coriolis effect acts the way that it does. I encourage everybody in order to go view this video in order to learn more. The Coriolis force, as I mentioned, effectively deflects air to the right in the northern hemisphere and to the left in the southern hemisphere when you look from above. What this means is that air traveling from equator to pole tends to turn towards the east, whereas air moving from pole to equator tends to move towards the west. The final force that's important for atmospheric dynamics is the gravitational force. This is an equation that describes Newton's law of gravity. You don't really have to memorize this, but what you want to take home is that gravity always works towards the center of mass of a large object such as the sphere. So in this case, an air parcel is drawn towards the center of the sphere with some force. Alright, let's talk about force balance in the horizontal. Now, since gravity always works in the vertical direction, it turns out that it's not relevant for an analysis of how air movement acts in the horizontal direction. In the horizontal, air parcels are primarily dominated by Coriolis force and pressure gradient force. Now, because of the fact that we have higher temperatures at the equator and cooler temperatures at the poles, this tends to give rise to pressures that decrease as you go from equator to pole. Now, what's going to happen to a fluid parcel in that case? Well, if a fluid parcel in the subtropics, for instance, is simply sitting still, it'll experience a pressure gradient force which acts to push that fluid parcel towards the poles. As it experiences this force, it then experiences an acceleration. This acceleration simply means that the speed of the air parcel will increase as it is moving closer and closer towards the polar regions. As that air parcel is moving faster and faster, it then experiences a Coriolis force. It turns out that the Coriolis force is proportional to the velocity of the air parcel. So the faster that air parcel is moving, the stronger the Coriolis force it experiences. Now, that Coriolis force always acts to the right of the direction of motion of the fluid parcel. So as that Coriolis force continues to act more strongly, the air parcel is going to be turned to the right in the process. And Coriolis will continue to strengthen as the air parcel continues to accelerate and experiences a higher velocity. At some point, the Coriolis force and the pressure gradient force will end up acting in opposite directions to one another while the air parcel moves directly to the east, or along lines of constant geopotential / lines of constant pressure. What this means is that in geophysical flows, that is, flows where you have a rotating object such as the Earth, that the air parcels will tend to move along lines of constant pressure. That is, they won't move from high pressure to low pressure, but will instead move along lines of constant pressure. This creates a very interesting dynamic in the atmosphere because it means that air will generally move from west to east in the mid-latitudes, hence giving rise to the storm track that we experience in the mid-latitudes. In the vertical, the fluid parcels are dominated by a balance between pressure gradient force and gravitational force. Now you might be thinking, if gravity is always acting towards the center of the Earth, why doesn't the whole atmosphere effectively compress into a very, very thin layer right by the Earth's surface as it's being pulled downward? Well, it's again a matter of force balance. The forces acting on those fluid parcel include both pressure gradient force and gravity. Now, gravity acts to pull the fluid parcel downward, but it's also experiencing a pressure that is acting upward on the fluid parcel. Now, the sum of the force acting upward has to balance the force acting downward from gravity and the pressure gradient force acting downward as well. Effectively, what this means is that the air pressure below the fluid parcel needs to be stronger than the air pressure above the fluid parcel in order for that fluid parcel to not move up and down. This state of not moving up and down is a state known as hydrostatic balance, and it effectively is this force balance then between gravitational force and pressure gradient force. Because of the fact that you need to have more pressure acting to push the fluid parcel upward, that means that the pressure underneath the fluid parcel needs to be larger than the pressure on top of the fluid parcel. This is effectively why we have that air pressure decreases as you go up in altitude. That is, as you go higher and higher and higher, we must have the pressure that is being experienced at those altitudes must decrease as you go higher and higher. Consequently, we have the highest fluid pressures near the Earth's surface, which kind of makes sense if you consider the air is being pulled down towards the Earth's surface, with air pressure decreasing as you go to higher and higher altitudes. The vertical structure of the atmosphere reflects this pressure decrease very clearly. Namely, we have our highest pressure of about 1,000 hectopascals near the Earth's surface and an exponential decay of air pressure as you go up in altitude. Again, this decrease in air pressure is purely due to the force balance associated with hydrostatic balance in the atmosphere.